Hello and welcome to this video on quadratic inequalities. So we've been posed a question to find all integers for which x squared is less than or equal to 2x plus 15. Now a very inefficient way of doing that would be to choose values of x, as I have here from -5 to 7, work out the value of x squared and the value of 2x plus 15, and then compare the values of x squared and 2x plus 15 to find out when x squared is less than or equal to. So when x is -5, x squared is 25, and 2x plus 15 is 5, which obviously means that x squared is larger. And that is the same for -4 as well. X squared is larger than 2x plus 15. When x is -3, x squared and 2x plus 15 have the same value of 9, so it is therefore true. And it's true all the way down to when x is 5, when again x squared and 2x plus 15 both have the same value, in this case 25. For all the other integer values between -3 and 5, x squared is less than 2x plus 15, and then for x is 6 and x is 7, x squared is larger than 2x plus 15. So the integers are all the integers between -3 and 5. This was, however, a very inefficient way of solving this problem. So what I've done instead is to solve the quadratic inequality. I've subtracted 2x and 15 from both sides to make the right hand side 0. I factorised it to give me x plus 3 and x minus 5. And the critical values which make it equal 0 are -3 and 5. And then we can see from the curve that -3 and 5 are where the curve cuts the x-axis, and all the values between -3 and 5 are the values which give us x squared minus 2x minus 15 as less than or equal to 0. So in terms of all the values of x which solve that, they're all the values between -3 and 5 inclusive. In general, if we have a positive x squared and the inequality is less than 0, then that means that we're looking at the values in between the critical values. So here the critical values are -2 and 8, and our solutions are between -2 and 8, which is one region of the number line. Alternatively, if x squared is positive and the inequality is greater than 0, then we have two regions either side of our critical values. So all the values when x is less than -2, and all the values when x is greater than 8. So this is two regions on our number line. So here's an illustration of this concept. So when x squared is positive and it's less than 0, our critical values -2 and 8, and the region we want, where x squared minus 6x minus 16 is less than 0, is between the critical values. However, when x squared is positive and the inequality is greater than 0, we can see that we get two regions on our diagram either side of the critical values, as indicated by the two arrows on the diagram. Here's another example. To find all the possible values of x which x plus 3, x plus 4 is greater than 110. Well, neither side of the inequality is equal to 0, so that's our first objective. So we expand the brackets, subtract 110, and we get x squared plus 7x minus 98 is greater than 0, which we can factorise, and the critical values are -14 and 7. But notice that the quadratic equation that we solved, x squared plus 7x minus 98 is greater than 0. It's a greater than, so it means that the regions we want are either side of the critical values, so they are x is less than -14 and x is greater than 7. In this example, we've been asked to describe all the numbers which satisfy two inequalities. X squared is less than 5x plus 14, and 5x minus 1 is greater or equal to 14. So firstly, working on the quadratic, we need to make the right hand side 0 with a positive x squared on the left. The critical values are -2 and 7. The inequalities are less than, so it's the in-between region, -2 to 7. For our linear inequality, we simply need to add 1 and divide by 5, and we get that x is greater or equal to 3. But we need to find the numbers which satisfy both. A good way of looking for the answer is to draw a number line and put our inequalities on it. So for -2 to 7, I've drawn a line between -2 and 7 with two empty circles to represent the fact that they can't be equal to. And for x is greater or equal to 3, we have a filled in circle at 3 with an arrow going to the right. And we're looking for any parts of the diagram, any parts of the number line where we have two lines at the same time. And that's true between 3, which includes 3, and up to 7, but not including 7. So the final answer, as shown, is that 3 is less than or equal to x is less than 7, and it's one region. And just to let you know, alongside this video, we have notes on these inequalities. Just a little recap. So we have 4 inequalities, all starting x squared plus 5x plus 4, but each one is slightly different. The first one is greater than 0, the second one is less than or equal to 0, the third one is greater than or equal to 0, and the last one is less than 0. By factorising and solving, or by looking at the graph, we can see that the critical values are -4 and -1, from which we get different answers for each one. So for the first one, it's an either side, it's a greater than, so x is less than -4 or x is greater than -1. For the second one, it's less than or equal to 0, it's an in between, so it's in between our critical values, so -4 is less than or equal to x is less than or equal to -1. For the third one, again it's a greater than or equal to, so that's an either side, so x is less than or equal to -4 or x is greater or equal to -1. And for our final one, it's less than 0, it's in between, so it's -4 is less than x is less than -1. This example is similar to a previous one, except it's in context. So we have a rectangle with sides of 2x plus 3 centimeters and x minus 1 centimeters. We're told that the perimeter is more than 22 centimeters, but the area is no more than 52 centimeters squared. Define all the possible values of x. So starting with the area is no more than 52. That means it's less than or equal to 52. And the area of the rectangle is given by 2x plus 3x minus 1. So expanding the brackets and taking away the 52, we can factorize it. The critical values are -11/2 and 5. And because it's a less than or equal to, it's an in between. X is in between -11/2 and 5, and it can be equal to those values. For the perimeter, it's more than 22. Well, the perimeter of a rectangle is given by 2 times each of the sides added together. So 2 lots of 2x plus 3 plus 2 lots of x minus 1. That is greater than 22. Simplifying it, we get that x is greater than 3. So once again, I've used the number line to find my final answer. I've illustrated both of the inequalities on the number line, and we can see that x must be greater than 3, but less than or equal to 5. Back on the note sheet, we have another example with a context, a rectangular garden, and again we're considering the area and perimeter, and we can combine those together to get our final answer. We'll finish off with some questions for you. So in question 1 we have 5 inequalities to solve, and in question 2 we have another of these contextual examples with the rectangle and the area and perimeter. And here are the answers to those questions. Thank you for listening.